Dr. R. Sugurat Samuel is working as professor in physics in SRM University, Chennai. He is also training students for IIT JEE, AIEEE, and BITSAT. He has more than 16 years of academic experience both in teaching and research. He has published a book titled The Complete Handbook of Bachelor of Electronic Science Practicals. It is prescribed book in the syllabus for BSc Electronic Science by University of Madras. He has attended and presented papers in several national and international conferences and conducted many training programs and workshops. He has experience in both regular classroom teaching and also online teaching. His research areas are ultrasonics, polymers, crystal growth, and photovoltaic systems.
Welcome to UG's lecture series on Applied Sciences Electronics. We have been listening to a series of lectures on the subject Electricity and Basic Electronics for the BSc Electronic Sciences course. This paper is the first paper in the first semester. This lecture is the 42nd lecture in the series. We have been discussing about the applications of transistor in this part of the lecture. Before we start today's lecture, let us see the session outline for today's lecture. In this session, we are going to see the transistor as a device, especially as an amplifier, and how to draw a load line and how to fix a Q point. So, drawing of load line and fixing of Q point we are going to see in this lecture. First, how to use transistor as an amplifier, that we need to learn. In the last lecture, we have seen one application of the transistor, that is a switch. The transistor was driven to the saturation region and the cutoff region to make it act as a switch. But in the case of amplifier, it should not be driven to the extreme regions, but it should be kept in the active region. How it is done? We need to learn the technique for keeping the transistor in the active region. Let's see how a transistor is used as an amplifier. Before that, we need to quickly have a look at the circuit diagram of the active characteristics or dynamic characteristics of a transistor with resistors and the input connected to the transistor. This is a familiar diagram for us now. We have analyzed this circuit for the previous application, transistor as a switch. It is once again given here so that we have a look at this circuit, and any equation, if it is written from this diagram, we will be able to have a better understanding. And as I have already mentioned, we have this RB connected, RC connected additionally to the static characteristics of a transistor, and also a Vi is given. The RC is connected here so that we could draw the output across that. So, these are the modifications done to the regular characteristics, the static characteristics circuit of a transistor. Now, it is ideal time for us to see how a transistor is kept in the active region to make it use as an amplifier. Transistor as an amplifier. For using the transistor as an amplifier, we will use the active region of the VO versus Vi curve, which we have already seen in the previous lectures. The slope of the linear part of the curve represents the rate of change of the output with the input. I hope you could bring it back to your mind, the graph that we have drawn for the VCE versus VBE in the last lecture. Actually, VCE was the output voltage and VBE was the input voltage. So, here in this lecture, we represent them as the output and input voltage. What is the relation between them was very much shown in the characteristics curve. So, let us have a look at the graph once again and see where the active region is appearing and what is the trend of the curve in that region. This is how we have drawn the graph in the previous lecture. VCE is the output voltage and VBE is the input voltage. The transistor was driven from the cutoff region to the saturation region, and again to the two regions it was made to work, and in between we have this active region. In the active region, the transition is happening. When we have a look at the slope of this line in the active region, it has a negative slope. We have in the y value the output and the x value is the input. When we take the slope directly, we will be able to find the voltage gain or voltage amplification. In the previous lecture, we have not given much importance to this transition region, that is here as active region, because we wanted the transistor work either in the cutoff region or in the saturation region. But here as an amplifier, the transistor finds use only in the active region. So, we need to find the conditions for the transistor to be kept in the active region every time. But what is the significance of the slope? The slope gives the voltage gain or the voltage amplification, because it is the ratio of output voltage to the input voltage. And one more thing we need to notice here, the slope is a negative value. What is the implication of this negative value that we get? Does it have any significance? It very much has some significance. We will see what it is. The slope is negative because the output is written as VO is equal to VCC minus ICRC. This equation is the outcome of the Kirchhoff's voltage law for the output side. And when we take the change on the output voltage, for that we have to differentiate this equation. The differentiation, the mathematical things are not very much highlighted here, but when we take the differentiation, when we differentiate this equation, there is a change in the VO, but VCC is a constant. So, we cannot differentiate. When you differentiate, we get only 0. So, it is not shown here in this equation. And ICRC, when we differentiate, again RC is a constant, but IC only will change. So, this is the equation we have. Delta VO is the change in the voltage, output voltage, which has got a negative sign. That is why the input voltage of the CE amplifier increases its output voltage as the output voltage decreases, and the output is said to be out of phase with the input. What is the meaning of out of phase? When one quantity increases, the other quantity also would increase, but the trend is negative. That is the meaning of out of phase. In oscillations and waves and also in optics and all the topics, we come across this phase very often. Here also we will be giving a sinusoidally varying voltage as the input for an amplifier. So, the phase concept is to be learnt. There will be a phase reversal of 180 degree happening in the case of an amplifier which is designed from using a transistor in the common emitter configuration. It is found only in the common emitter configuration. We are yet to learn about the common base configuration and common collector configuration. That small topic is still pending. So, those concepts we will be doing in the upcoming sessions. At that time, we will be able to compare the performance of a common emitter configuration with the common collector and common base configurations. We will do that analysis in the future lectures, but right now as we are going ahead with the circuits confined only to the common collector mode, let us keep this point in mind. The amplifier has a phase reversal. The input and output will have a phase reversal of 180 degree. This is in short called as out of phase. Now let us analyze the circuit further. If we consider the change in the output voltage, that is delta VO, and change in input voltage, that is delta VI, as small changes in the output and input voltages, then the ratio delta VO upon delta VI is called the small signal voltage gain, which is represented as A suffix V. Here A implies the amplification and V implies the voltage. So, voltage amplification of the amplifier. If the VBB voltage has a fixed value corresponding to the midpoint of the active region, the circuit will behave as a CE amplifier. We can express the voltage gain AV in terms of the resistors in the circuit and the current gain of the transistor as follows. How the circuit analysis is done? As I have already shown the circuit and application of Kirchhoff's voltage law for the two loops on the input and output side will become handy now. The same thing is done. Let's see how the voltage gain expression is obtained for the given circuit. These equations are now very familiar. This is the Kirchhoff's voltage law, which is applied for the output side, and when we differentiate we get this as the expression. Because VCC is constant, we have 0 here. In this expression RC is a constant, so the change in the current alone is highlighted. Similarly, for the input side, when we write, this is the equation we get. Here the VI is a variable, so it is shown with a delta VI. Here RB is a constant, only IB is a variable, so it is written as delta IB. VBE will also be varying, so it is also written as delta VBE. These are the two equations we need to consider, delta V0 and delta Vi. When we take the ratio of these two, we get the amplification, especially the voltage amplification. But we can make some approximations in the equations based on the values. If we could neglect one or two terms in the equation, that will reduce the simplification part. So, how the approximations are done to reduce the equation further? Let us have a look at the approximation. But delta VBE is very much negligibly small. It is the voltage change that is happening across the base emitter junction. Even for the base emitter junction, the voltage is very less, maybe 0.6 or around 1 volt. But the change when it is happening, it is very small, so it is negligible in comparison with this term IB RB. Here this term will be a governing term, it is very effective, this value will be very high. So, the delta VBE could be neglected in the expression. After doing so, we get the equations further reduced. So, the voltage gain of this CE common emitter amplifier is given by this expression. Delta V0 divided by delta Vi is written in this form. The minus sign is still intact because it has got a very significant meaning. So, it is written as such. It represents the phase reversal that is happening between the input and output voltage. So, we get a final expression like this: AV is equal to beta within bracket RC upon RB. How did we get this beta? Beta is the current gain, which is equal to delta IC divided by delta IB. This beta value we have already learnt in the previous lectures. So, let us analyze this final equation we have obtained after a short break. Welcome back. We have got an expression for the voltage gain in terms of current gain. That equation is a very useful equation. Let us have a look at the equation once again. This is the expression for the voltage gain. AV is equal to negative of beta multiplied with RC upon RB. So, the voltage gain is very much governed by the current gain, and also the ratio of the output resistance, or here it is collector resistance, to the input resistance, here it is RB. Beta is a very high value. This concept we have learnt in one of the earlier lectures. We have even got an expression relating the beta value and the alpha value. Alpha is the current gain in common base mode and beta is the current gain in the common emitter mode. These two have a relation. That relation we have derived. At that time we have got an idea about the beta value. It is a high value depending on the transistor. It could even vary from 50 to 1000. So, as beta is high, the voltage gain will also be reasonably high in the case of an amplifier which is designed using a transistor in the common emitter mode. Let us see what is the use of this amplifier and how it is to be kept in the active region. Thus, the linear portion of the active region of the transistor can be exploited for the use in amplifier. As I have already mentioned, in the active region, the change is happening, the transition is happening from the cutoff to saturation or saturation to cutoff, but that change is very linear over a particular range. If we are able to keep the transistor in that linear range, then the transistor could be used as an amplifier. That is what we have seen now. It is time for us to see how to keep this transistor in the active region. It should not be driven to the extremes, that is the saturation and cutoff region. We have to maintain it in the active region to enable the amplifier work properly. How it is done? For that, we need to consider a line called load line. We have to draw a load line on the output characteristics curve, and then we have to fix a point. Any variation that is happening should happen with respect to that particular point. That point is called Q point. So, let us learn the concepts related to the load line and Q point. Designing of an amplifier. The designing of transistor as an amplifier in CE configuration requires few more technical aspects to be considered. We have to fix an operation point, which is also called Q point, by drawing a load line on the output characteristics to fix the permissible range of its operation. The load line. What is a load line? It is very much used to fix the Q value. First, let us learn what is a load line and then how to draw a load line on the output characteristics curve. Load line is used in graphical analysis of electronic circuits, representing the constraints other parts of the circuit place on the device, like transistor. We shall now learn how a load line is drawn on the output characteristics graph for fixing the range of operation of the transistor amplifier. For the given values of the load resistance RC and supply voltage VCC, 2 points, namely A and B. Here A is VCC, 0 and B is 0, VCC divided by RC, are located on the axis of the VCE and IC respectively. A load line is obtained by joining the 2 points A and B. We have seen what are the 2 points we need to consider on the 2 axes, a point A and a point B. Point A is chosen on one axis. It is done on the x-axis. What is the x-axis? It is the VCE axis. And point B is marked on another axis, that is on the y-axis. which is a VCE axis. How these 2 points are chosen and how the line is drawn, we will be able to understand fixing of these points only when we have a look at the graph. Let's have a look at the graph. This is how it is done. The point A is VCC comma 0 and this point is 0 comma VCC divided by RC. What is the importance of these two values that we have chosen? Because the point A is on the x-axis, y value is 0. The point B is on the y-axis, so x value is 0 for it. This VCC is the maximum value possible on the VCE axis because it is the biasing voltage. That is the maximum value. Similarly, the VCC divided by RC, this ratio will give us the current, that is IC, that is the maximum current. So, what is the meaning of these 2 points? These 2 points fix the extreme values of the voltage and the current respectively on the voltage axis and the current axis. Once we have these ideas in mind, then fixing the 2 points will not be very difficult. Y VCC comma 0, Y 0 comma VCC by RC. It is easy now for us to say the extreme values of the current and voltage possible in the circuit. Once it is fixed, we need to fix a point, the point of operation for us. So, let us have a look at the diagram once again, how the points are drawn on the output characteristics and connected. So, this is how the 2 points, the extreme voltage and extreme current values are connected by drawing a line. This line is called the load line. Now, the load line is drawn. Here we have taken a point Q, which is called the operation point or quotient point. What is the importance of this quotient point? We will learn the importance of this, but right now we have some idea about this. It is somehow chosen in the middle on a particular IB value. All these lines are for different values of IB, but one particular IB we can choose maybe a middle value and fix a point called Q point. Now, we have learnt how a load line is to be drawn and what is the importance of that line. Mainly the load line is drawn to enable us to fix a point called Q point. The Q point is the operating point of the transistor. We should make the transistor work around the Q point. It is very difficult to make the transistor work exactly at the Q point with the fixed values. Maybe there is a change, but that change should happen around the Q value. Let us see what is the importance of making it work around the Q value. The point of intersection Q of this line, the load line, on the active region of the output characteristics with a suitable value of the base current, which is here marked as IBQ, such that the output voltage is symmetrical, is called an operating point or quotient point for the amplifier. This IBQ is the input base current and the corresponding values of VCE and IC are also marked as Q. So, VCEQ is the collector to emitter voltage and ICQ is the collector current respectively at the operating point. Proper fixing of the Q point helps us to get an understanding, to get an undistorted output signal. We shall discuss about this in the future sessions. What is the meaning of the undistorted signal? We will be able to learn about the operation of a transistor as an amplifier only when we give an input and take an output, especially a varying input, and the output will also be varying accordingly. When these variations are happening, it should happen with respect to a fixed point. That fixed point is only the Q point. So, it is very much essential for us to fix the Q point when we design a transistor amplifier in the CE configuration. So, that is what we have learnt now. Let us have a look at the operating point in the output characteristics curve and try to see how the VCEQ and ICQ are all marked. After fixing the Q point, we have three important values. One is the IB at Q, and the VCE at Q, and IC at Q. So, the changes in the output voltage will happen around this VCEQ, and similarly the current will also be varying around this IC. It is done for a particular IB, so the IB should also be varying around this value. Once we fix this Q value, we should ensure the input is given in this range. If we give the input value which does not fall into this range decided by the Q, what will happen? The signal that we give will get distorted. We will be able to learn about the distortion, the perfect amplification, all that when we learn the transistor as an amplifier, that's called a single stage amplifier. For that, we need to first ensure a biasing. We need to learn about how a transistor could be biased using a single power supply or a single source, and then how to give the input and how to take the output practically. So, that is done in a separate topic that we will learn under the topic called single stage amplifier. When we give a varying input signal, the output signal also will be varying. What about the response? Can an amplifier amplify for a large range of frequency? All that we will be able to analyze when we learn about the single stage amplifier. So, right now we have got an idea about the Q point, drawing load line and fixing a Q point. How the Q point will act as a pivotal point in the case of amplification. Let us have a look at the diagram and we will have an idea. This is how the Q point will decide the output signal. See here, in the x-axis we have taken the input current and in the y-axis we have taken the output current. It is not voltage current graph, it is the current versus current graph, input current and output current. When the input current is given as a varying one with respect to the Q point, the output current is also varying with respect to the Q point again. But there is an amplification done, because when we look at the ranges, it is in the microampere range, here it is the milliampere range, the output is in the milliampere range. So, there is a current amplification possible. This is how the Q factor, the Q value decides the amplification done in an amplifier. Let us have the summary of today's lecture. In this lecture, we have seen the transistor as a device, especially amplifier, and how to draw a load line and how to fix a Q point. These concepts we have learnt today. Let us test our understanding by answering these questions. In which region is a transistor used as an amplifier? Explain the functioning of transistor as an amplifier. What are the load line and Q point? Explain their significance. With this, I wind up today's lecture. In the upcoming lecture, we will analyze the common collector and common base configurations of the transistor and compare them with the common emitter configuration. It is high time for us to finish that topic which is pending for long. With this, I wind up this unit. Thank you for listening.